Welcome! Need some gentle help with getting to sleep? You are in the right place and have made an excellent decision to listen to a compilation of facts combined to tell a bedtime story for sleepy adults, all about our own solar system to help you sleep. Let's begin. Part 1. A serene journey begins. Welcome to our solar system. We are going on a peaceful journey together, a slow and soothing exploration among the stars. There is no need to hurry. There is nowhere else you need to be. Just here, now, watching and listening as we begin to wander through the vast, quiet reaches of our solar system. Our solar system is an ancient place, born roughly 4.5 billion years ago from a swirling cloud of gas and dust. Imagine that cloud, slowly turning in the darkness of space, collapsing gently inward under its own gravity. Over countless millions of years, that cloud grew denser at its center, warming and brightening until it ignited into the sun we know today. Around that newborn star, the remaining dust and gas gathered into clumps, forming planets, moons, asteroids, and comets. Everything we will visit together on this journey came from that same ancient cloud, all of it connected, all of it part of one family orbiting our sun. The solar system is larger than most of us can easily imagine. If you were to travel outward from the sun at the speed of light, the fastest speed possible, it would take you just over 8 minutes to reach Earth. To reach Neptune, the farthest major planet, would take more than 4 hours. And beyond Neptune, far beyond, lies a vast halo of icy objects that stretches nearly halfway to the nearest star. But now we do not need to measure these distances with numbers. We can simply let ourselves feel the vastness, the deep silence, the patient turning of worlds in their orbits. Our solar system contains 8 major planets, each one unique, each one holding mysteries and wonders. Closest to the sun we find the small, rocky worlds: Mercury, Venus, Earth, and Mars. These planets have solid surfaces you could stand upon if you could somehow survive some of the extreme conditions. Farther out, beyond the orbit of Mars, lies a belt of asteroids, remnants from the early solar system that never quite formed into a planet. Beyond that belt, we enter the realm of the giant planets, Jupiter and Saturn, enormous spheres of gas and liquid with no solid ground beneath their swirling clouds. And then Uranus and Neptune, the ice giants, cold and distant and wrapped in deep blue atmospheres. Each planet moves in its own elliptical path around the sun, tracing the same route over and over again year after year, century after century. Some planets orbit quickly, completing their yearly journey in just a few Earth months. Others take decades or even centuries to make one slow circuit around the sun. And as the planets orbit, many of them spin on their axes, turning day into night and night into day. Some spin quickly, some slowly, and one even rolls on its side as it travels through space. Between and among the planets, hundreds of moons travel in their own orbits. Some of these moons are tiny, jagged rocks only a few miles across. Others are larger than the planet Mercury, with thick atmospheres, hidden oceans, and landscapes that rival the planets themselves in complexity and beauty. There are moons with geysers that shoot water into space, moons covered in smooth ice, moons scarred by countless craters, and moons with methane lakes and rivers. Each moon is a world unto itself, quietly circling its planet as the planet circles the sun. And beyond the planets and their moons, in the cold outer reaches of the solar system, drift the comets. These icy wanderers follow long, stretched-out orbits that carry them far from the sun and then swing them back again, sometimes after thousands or even millions of years. When a comet approaches the sun's warmth causes its ice to vaporize, creating a glowing halo and a long, flowing tail that stretches across the sky. Ancient people saw these tails and called them omens. Today we understand them as beautiful reminders of the solar system's icy frontier. All of this, every planet and moon and asteroid and comet, all of it belongs to the Sun. The Sun is the heart of our solar system, the source of light and warmth and gravity that holds everything in place. Without the Sun, there would be no Earth, no life, no us. The Sun contains about 99.8% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids and comets and dust, together make up less than 0.2%. The Sun's gravity reaches out across billions of miles, gently holding distant comets in their orbits, keeping the planets in their paths, and maintaining the delicate balance that has existed for billions of years. Part 2. The Heart of Light, our Sun. At the center of our solar system burns a star, our Sun, a sphere of light so bright and vast that it holds within it nearly all the mass of everything that orbits around it. The Sun is not the largest star in the universe, nor the brightest, but it is ours, and it has been shining steadily for more than 4.5 billion years. Every sunrise you have ever seen, every warm afternoon, every glimmer of light on water, every shadow cast by a tree, all of it has come from this single, patient star. The Sun is enormous beyond our everyday experience. If you could line up more than 100 Earths side by side, they would just stretch across the Sun's diameter. If you could hollow out the Sun, you could fit well over 1 million Earths inside it. And yet, for all its size, the Sun is made of surprisingly simple materials, mostly hydrogen, about 73% by mass, with about 25% helium, and just traces of heavier elements like oxygen, carbon, iron, and neon. It has no solid surface, no ground to stand on. It is a sphere of glowing gas and plasma, held together by its own immense gravity, constantly churning and shimmering with energy. Deep within the Sun's core, where temperatures reach about 15 million degrees Celsius and the pressure is almost unimaginable, hydrogen atoms collide with such force that they fuse together, forming helium and releasing vast amounts of energy in the process. This process, called nuclear fusion, is what makes the Sun shine. Every second the Sun converts roughly 4 million tons of matter into pure energy. That energy travels outward from the core, moving slowly at first through dense inner layers where it can take tens of thousands of years to work its way out, then faster as it reaches the surface, and finally radiating out into space as light and heat. It takes light just 8 minutes and 20 seconds to travel from the Sun's surface to Earth, a journey of about 93 million miles. The surface of the Sun, called the photosphere, is a roiling, bubbling layer of gas with a temperature of about 5,500 degrees Celsius. If you could observe the Sun closely through a safe telescope, you would see it is not smooth or uniform. The surface is covered in a granular pattern, like a field of bright cells separated by darker boundaries. Each granule is about the size of the U.S. state of Texas or larger, and represents a convection cell where hot gas rises from below, cools slightly, and then sinks back down. The granules are constantly forming and disappearing, each one lasting only about 10 to 20 minutes before being replaced by new ones. Dark patches called sunspots appear and fade on the photosphere, marking regions where the Sun's magnetic field is especially strong and the surface is slightly cooler, though still extremely hot by any normal standard. Sunspots can be larger than Earth, and they tend to appear in groups. The number of sunspots visible on the Sun changes in a fairly regular cycle of about 11 years. At solar maximum, the Sun may have many large sunspot groups and be especially active. At solar minimum, there may be days when no sunspots are visible at all. Above the photosphere lies the Sun's atmosphere. The lowest layer, the chromosphere, glows with a reddish light that comes from hydrogen gas, though it is usually invisible because the photosphere is so much brighter. Above the chromosphere stretches the corona, a vast halo of extremely hot, tenuous gas that extends millions of miles into space. The corona is astonishingly hot, with temperatures reaching 1 to 3 million degrees Celsius, far hotter than the surface below it. During a total solar eclipse, when the moon passes directly between Earth and the sun and blocks the brilliant photosphere, the corona becomes visible as a shimmering, pearly crown around the darkened sun. It is one of the most beautiful sights in nature, a rare glimpse of the sun's outer atmosphere. The sun is not silent or still. It constantly sends out a stream of charged particles called the solar wind, a flow of electrons and protons that rushes outward in all directions at speeds of about 300 to 800 kilometers per second, filling the solar system. When these particles reach Earth, they interact with our planet's magnetic field, sometimes creating the auroras, those shimmering curtains of green and red and purple light that dance across the polar skies. The solar wind travels far beyond Earth, all the way to the edge of the solar system, where it finally mingles with the thin gas between the stars. The sun is about halfway through its life. It has been shining for roughly 4.6 billion years, and it has enough hydrogen fuel in its core to continue shining at roughly its current brightness for another 5 billion years or so. In another 5 billion years, it will begin to run out of hydrogen fuel in its core. When that happens, the core will contract and heat up, while the outer layers will expand, and the sun will become a red giant, swelling to perhaps 100 times its current size. But all of that is far, far in the future. For now, the sun shines steadily, warming our world, driving the weather, nourishing life, and lighting the days. Part 3: Swift Mercury, the sun's closest companion. Let us journey now to the innermost planet of our solar system, a small, swift world that races around the sun in just 88 Earth days. This is Mercury, the closest planet to our star. A world of extremes, a place where the sun looms enormous in the sky and temperatures swing wildly between scorching heat and freezing cold. Mercury is a world of silence and stillness, airless and ancient, its surface scarred by billions of years of impacts from space. Mercury is small, the smallest of the 8 major planets. If you could hold Earth in one hand and Mercury in the other, Mercury would feel tiny by comparison, only slightly larger than our moon. Its diameter is about 4,800 kilometers, less than half the width of Earth. Despite its small size, Mercury is dense and heavy for its dimensions. Scientists believe that beneath its rocky surface lies a large iron core, making up about 60% of the planet's total mass. This iron heart gives Mercury a higher density than any other planet except Earth. The surface of Mercury is gray and cratered, resembling our moon in many ways. Billions of years ago, when the solar system was young and chaotic, asteroids and comets struck Mercury's surface again and again, leaving behind craters of all sizes. Some of these craters are small, just a few meters across. Others are enormous. The largest known crater on Mercury is called the Caloris Basin, a vast impact scar more than 1,500 kilometers wide. The collision that created the Caloris Basin was so powerful that it sent shock waves through the entire planet, creating strange, jumbled terrain on the opposite side of Mercury. Between the craters, you can see smooth plains of ancient lava that flowed across the surface billions of years ago, filling in low areas and creating flat expanses. Mercury was volcanically active in its distant past, though today it is quiet and geologically dead. The surface also shows long, winding cliffs called scarps, some of them hundreds of kilometers long and up to 3 kilometers high. These scarps formed as Mercury's interior cooled and contracted over time, causing the planet's crust to wrinkle and buckle like the skin of a drying apple. Mercury orbits the Sun at an average distance of about 58 million kilometers, much closer than Earth's 93 million kilometers. Because it is so close to the Sun, Mercury moves quickly through space, traveling at an average speed of about 47 kilometers per second. This is faster than any other planet. The ancient Romans named this swift-moving planet after their messenger god, Mercury, who wore winged sandals and carried messages between the gods. One of the strangest things about Mercury is the relationship between its day and its year. Mercury rotates on its axis very slowly, taking about 59 Earth days to complete one full rotation. At the same time it orbits the Sun in 88 Earth days. These two periods are related in an unusual way. Mercury rotates exactly 3 times for every 2 orbits around the Sun. This means that a single day on Mercury, from one sunrise to the next sunrise, actually lasts 176 Earth days, or 2 Mercurian years. If you could stand on Mercury's surface and watch the Sun, you would see it move very slowly across the sky, taking months to rise, arc overhead, and set again. Because Mercury has almost no atmosphere to trap and distribute heat, temperatures on the planet vary enormously between day and night. On the side facing the Sun, the surface can reach about 430 degrees Celsius, hot enough to melt lead. On the night side, with no sunlight and no atmosphere to hold warmth, temperatures plummet to about -180 degrees Celsius. This temperature range of more than 600 degrees is the greatest of any planet in the solar system. At Mercury's poles, deep inside some craters where sunlight never reaches, scientists have found evidence of water ice, frozen and preserved in permanent shadow despite the nearby scorching heat. Mercury has only a very thin atmosphere, so tenuous that scientists call it an exosphere rather than a true atmosphere. This exosphere is made up of atoms blasted off the surface by the solar wind and by micrometeorite impacts. It contains trace amounts of oxygen, sodium, hydrogen, helium, and potassium, but the total amount of gas is so small that it provides no protection from radiation or meteorites and creates no weather or wind. Standing on Mercury, you would see a black sky even in daytime, with stars visible alongside the brilliant Sun. For much of human history, Mercury was known only as a bright point of light visible near the Sun at dawn or dusk. It is difficult to observe because it never strays far from the Sun in our sky, and it is often lost in the Sun's glare. The first spacecraft to visit Mercury was Mariner 10 in the 1970s, which flew past the planet 3 times and photographed about 45% of its surface. Decades later, the Messenger spacecraft orbited Mercury from 2011 to 2015, mapping the entire planet in detail and making surprising discoveries, including the water ice at the poles. Despite being so close to the Sun, Mercury holds many mysteries. Scientists are still working to understand its large iron core, its magnetic field, which is unusual for such a small planet, and the history of volcanic activity on its surface. Mercury reminds us that even the smallest worlds can be complex and full of surprises. Imagine Mercury's silence, its stillness, its ancient craters holding their shapes for billions of years. Mercury's patient orbit repeats endlessly. Part 4, Veiled Venus, a world of clouds and mystery. We travel outward now from Mercury, moving farther from the Sun to the second planet, a world wrapped in thick clouds that hide its surface from view. This is Venus, named for the Roman goddess of love and beauty, and called the evening star or morning star because of its brilliant appearance in Earth's sky. Venus is almost the same size as Earth, a twin in dimensions, but beneath its bright clouds lies a world utterly different from our own, a place of crushing pressure, searing heat, and slow, backward rotation. Venus is the brightest object in the night sky after the Moon. Ancient peoples noticed this bright, wandering star and gave it special significance. The planet shines so brightly because it is covered in highly reflective clouds made of sulfuric acid droplets that reflect about 75% of the sunlight that reaches them. These clouds completely enshroud the planet, forming a thick layer that extends from about 50 to 70 kilometers above the surface. Below the clouds lies an atmosphere so dense and hot that no human-made spacecraft has survived on the surface for more than a couple of hours. Venus orbits the Sun at an average distance of about 108 million kilometers, closer to the Sun than Earth, but not dramatically so. It completes one orbit in about 225 Earth days. But Venus rotates on its axis extremely slowly, and uniquely among the major planets, it rotates backward compared to most other planets. While Earth and most planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. This backward rotation is called retrograde rotation, and scientists are not entirely sure why Venus spins this way. It may have been knocked into retrograde rotation by a massive collision early in its history, or its thick atmosphere may have gradually altered its spin over billions of years. Venus takes about 243 Earth days to complete one rotation on its axis, which means a day on Venus is longer than a year on Venus. Because of the combination of its slow retrograde rotation and its orbital motion, a solar day on Venus, from one sunrise to the next, lasts about 117 Earth days. If you could stand on the surface and watch through the clouds, you would see the sun rise in the west and set in the east, moving slowly across the sky over many weeks. The atmosphere of Venus is about 90 times denser than Earth's atmosphere, roughly equivalent to the pressure you would experience if you dove about 1 kilometer deep in Earth's oceans. This atmosphere is made mostly of carbon dioxide, with clouds of sulfuric acid and trace amounts of nitrogen and other gases. The thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that the surface temperature reaches about 470 degrees Celsius, hot enough to melt lead and hotter even than Mercury's sunlit side, despite Venus being much farther from the Sun. This makes Venus the hottest planet in the solar system. Beneath the thick clouds, the surface of Venus is hidden from view in visible light, but radar instruments on spacecraft have mapped the terrain in detail. The surface is mostly smooth plains of solidified lava, covering about 80% of the planet. There are also highland regions, some rising several kilometers above the average elevation. The two largest highland regions are Ishtar Terra in the northern hemisphere and Aphrodite Terra near the equator. Ishtar Terra contains Maxwell Montes, the tallest mountain on Venus, rising about 11 kilometers above the average surface level, taller than Mount Everest above Earth's sea level. Venus has hundreds of volcanoes scattered across its surface, some of them enormous shield volcanoes similar in shape to those in Hawaii, but much larger. The largest volcano, Mount Mons, rises about 8 kilometers high. Scientists believe that Venus was volcanically active in the relatively recent past, perhaps as recently as a few million years ago, and some evidence suggests volcanic activity may continue today. The surface shows vast lava flows, dome-shaped volcanic features, and channels carved by flowing lava that stretch for hundreds of kilometers. One surprising feature of Venus is that it has relatively few impact craters compared to Mercury or the Moon. Scientists have counted only about 1,000 craters on Venus's entire surface. This suggests that the surface is relatively young in geological terms, perhaps only a few 100 million years old. Something resurfaced Venus, covering over the older, more heavily cratered terrain. The most likely explanation is widespread volcanic activity that flooded the surface with lava, creating the smooth plains we see today. Whether this resurfacing happened gradually over time or in one or more catastrophic episodes is still debated. The weather on Venus is strange and extreme. The thick atmosphere circulates in a pattern called superrotation, where winds in the upper atmosphere race around the planet much faster than the planet itself rotates. At the cloud tops, winds can reach speeds of about 360 kilometers per hour, circling the planet in just 4 to 5 Earth days. Lower down near the surface, the winds are much slower, only a few kilometers per hour, but the dense atmosphere means these slow winds still carry tremendous force. Lightning flickers through the sulfuric acid clouds, and the entire atmosphere has a faint yellowish haze when viewed from the surface. Many spacecraft have visited Venus over the decades. The Soviet Venera program successfully landed several probes on the surface in the 1970s and 80s, sending back the only photographs ever taken from Venus's surface before the intense heat and pressure destroyed the spacecraft. More recently, orbiters like Venus Express and Akatsuki have studied the planet's atmosphere and weather patterns from space. These missions have revealed Venus to be a dynamic, active world, despite its hellish conditions. Venus reminds us that planets can take very different evolutionary paths. Venus and Earth began in similar ways, forming at similar times from similar materials. But something in Venus's history, perhaps its slightly closer proximity to the Sun or the loss of its water early on, set it on a path toward a thick carbon dioxide atmosphere and runaway greenhouse heating, while Earth developed oceans and a climate that could support life. Understanding Venus helps us understand the delicate balance that makes Earth habitable. Part 5. Our Blue Home. Earth in the Cosmos. We come now to the third planet from the Sun, the world we know most intimately, the only place in the universe where we know with certainty that life exists. This is Earth, our home, a blue and white sphere suspended in the darkness of space, covered with oceans and continents, wrapped in a thin atmosphere that makes all life possible. Earth is special not because it is the largest planet or the most dramatic, but because it is ours, and because it holds within it the conditions necessary for the extraordinary complexity we call life. Earth orbits the Sun at an average distance of about 150 million kilometers, a distance so convenient for reference that astronomers call it 1 astronomical unit. This distance places Earth in what scientists call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it, and Earth has water in abundance. About 71% of Earth's surface is covered by oceans, vast bodies of salt water that contain roughly 97% of all the water on the planet. The remaining water exists as fresh water in lakes, rivers, glaciers, ice caps, and underground aquifers, as well as in the atmosphere as water vapor. Earth completes one orbit around the Sun in approximately 365¼ days, which we call a year. The planet rotates on its axis once every 24 hours, giving us the cycle of day and night that structures our lives. Earth's axis is tilted about 23½ degrees relative to the plane of its orbit, and this tilt is responsible for the seasons. As Earth orbits the Sun, different parts of the planet receive more or less direct sunlight at different times of year, creating summer and winter, spring and autumn. Without this axial tilt, there would be no seasons, and the climate at any given latitude would remain constant throughout the year. The atmosphere of Earth is a precious envelope of gases held close to the surface by gravity. It extends about 100 kilometers above the surface before gradually fading into the vacuum of space, though most of the atmospheric mass is concentrated in the lowest 10 kilometers. The atmosphere is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with small amounts of argon, carbon dioxide, water vapor, and trace gases. This mixture is uniquely suited to supporting life. The oxygen we breathe is itself a product of life, released over billions of years by photosynthetic organisms like cyanobacteria and plants. Earth's atmosphere does more than provide air to breathe. It protects the surface from harmful solar radiation, burns up most meteorites before they reach the ground, and helps regulate temperature by trapping heat through the greenhouse effect. Without this natural greenhouse warming, Earth's average temperature would be well below freezing and the oceans would turn to ice. The atmosphere also creates weather, the constantly changing patterns of temperature, pressure, humidity, wind, and precipitation that shape our daily experience and drive the water cycle. Beneath the atmosphere lies Earth's surface, a dynamic patchwork of land and water. The continents are made of relatively light rock that floats on the denser rock of the mantle below. The ocean floors are made of heavier basaltic rock. All of this crust, both continental and oceanic, is broken into large pieces called tectonic plates that slowly move across the surface, driven by heat from Earth's interior. Where plates collide, mountains rise. Where they pull apart, new ocean floor forms. Where one plate slides beneath another, deep trenches and volcanic chains appear. This process, called plate tectonics, has shaped and reshaped Earth's surface over hundreds of millions of years. Earth has one natural satellite, the Moon, which orbits at an average distance of about 384,000 kilometers. The Moon is unusually large compared to Earth, about 1/4 the diameter of our planet. Scientists believe the Moon formed about 4.5 billion years ago when a Mars-sized object collided with the young Earth, throwing debris into orbit that eventually coalesced into the Moon. The Moon's gravity creates tides in Earth's oceans, causes our planet's rotation to gradually slow over time, and stabilizes Earth's axial tilt, which helps maintain a stable climate. Life on Earth is astonishingly diverse. From the deepest ocean trenches to the highest mountain peaks, from frozen polar regions to scorching deserts, from the dark caves beneath the surface to the upper atmosphere, life has found ways to survive and thrive. There are millions of species, perhaps tens of millions, each adapted to its particular environment. All life on Earth shares certain fundamental characteristics. All living things are made of cells, all use DNA to store genetic information, all require water, and all obtain energy through chemical processes. This suggests that all life on Earth descended from a common ancestor that lived billions of years ago. Earth formed about 4.5 billion years ago, along with the rest of the solar system. For the first few hundred million years, the planet was hot and inhospitable, bombarded by asteroids and comets. Gradually, the surface cooled, water vapor in the atmosphere condensed and fell as rain, and the first oceans formed. Somewhere in those ancient oceans, perhaps around hydrothermal vents on the ocean floor, or in shallow tidal pools, or in some other favorable environment, the first living cells emerged. These early organisms were simple, single-celled, and lived in a world very different from today, with no oxygen in the atmosphere and no life on land. Over billions of years, life evolved and diversified. Photosynthetic organisms began producing oxygen, gradually transforming the atmosphere. Multicellular life appeared. Plants and animals colonized the land. Dinosaurs rose and fell. Ice ages came and went. And eventually, in the very recent past by geological standards, humans appeared, developing language, culture, technology, and the ability to study and understand the world around us. Earth is the only world we know that harbors life, but it is not a sanctuary isolated from the rest of the solar system. Earth exists within a context, influenced by the sun's light and heat, protected by the moon's stabilizing presence, occasionally struck by asteroids or comets, bathed in the solar wind, connected through gravity to all the other objects orbiting the sun. Understanding Earth means understanding the solar system and our blue planet's place within it. Part 6: The Red Planet, Mars and its Ancient Secrets. We journey outward now beyond Earth's orbit to the fourth planet from the Sun, a world that has captured human imagination for centuries. This is Mars, the Red Planet, named for the Roman god of war because of its rust-colored appearance in the night sky. Mars is a cold, dry, dusty world, smaller than Earth, with a thin atmosphere and a surface marked by vast deserts, towering volcanoes, deep canyons, and polar ice caps. It is a world that may once have been warmer and wetter, and it may still hold secrets about the possibility of life beyond Earth. Mars orbits the Sun at an average distance of about 228 million kilometers, roughly 1.5 times Earth's distance from the Sun. It completes one orbit in about 687 Earth days, which means a Martian year is almost twice as long as an Earth year. Mars rotates on its axis once every 24 hours and 37 minutes, so a day on Mars, called a sol, is only slightly longer than a day on Earth. Like Earth, Mars has an axial tilt about 25 degrees, which gives Mars seasons similar to Earth's, though each season lasts about twice as long because of the longer Martian year. Mars is smaller than Earth, with a diameter of about 6,800 kilometers, roughly half the width of our planet. Its smaller size means lower gravity, about 38% of Earth's gravity at the surface. If you could stand on Mars, you would weigh much less than on Earth, and you could jump much higher. Mars has two small moons, Phobos and Deimos, named after the sons of the god Mars in mythology. These moons are probably captured asteroids, irregular in shape and heavily cratered. Phobos is the larger of the two, only about 22 kilometers across, and it orbits so close to Mars that it circles the planet 3 times each Martian day. Over millions of years, Phobos is slowly spiraling inward and will eventually either crash into Mars or break apart into a ring. The surface of Mars is predominantly reddish-brown, colored by iron oxide, essentially rust, in the soil and rocks. This rusty dust covers much of the planet and is occasionally whipped up into dust storms that can grow to encompass the entire planet, lasting for weeks or even months. When these global dust storms occur, they obscure the surface completely, turning Mars into a hazy orange sphere. Most of the time, however, the atmosphere is relatively clear and the surface features are visible. Mars has some of the most dramatic geological features in the solar system. Near the equator rises Olympus Mons, the largest volcano known anywhere. Olympus Mons is a shield volcano, similar in shape to the volcanoes of Hawaii but vastly larger. It stands about 21 kilometers high, nearly 3 times the height of Mount Everest, and its base is about 600 kilometers wide, roughly the size of the U.S. state of Arizona. The summit has a complex caldera, a collapsed crater about 80 kilometers across formed by ancient eruptions. Olympus Mons and the other large volcanoes on Mars have been extinct for millions of years, but their size tells us that Mars was once geologically active. Stretching across the Martian surface is Valles Marineris, a system of canyons that dwarfs Earth's Grand Canyon. Valles Marineris is about 4,000 kilometers long, up to 7 kilometers deep, and up to 200 kilometers wide in places. If this canyon system were placed on Earth, it would stretch across the entire United States from coast to coast. Scientists believe Valles Marineris formed partly through tectonic activity as the crust stretched and cracked, and partly through erosion and collapse. Some sections show layered sediments that may have been deposited by water or wind. Water is one of the great mysteries of Mars. The planet today is cold and dry, with an average surface temperature of about -63 degrees Celsius. The atmosphere is extremely thin, less than 1% the density of Earth's atmosphere, composed mostly of carbon dioxide with small amounts of nitrogen and argon. Liquid water cannot exist on the surface under these conditions because the atmospheric pressure is too low. Water would either freeze or evaporate immediately. And yet, the Martian surface is covered with features that look like they were carved by flowing water. Ancient river valleys, dried-up lake beds, fan-shaped deltas where rivers once emptied into larger bodies of water, and outflow channels where catastrophic floods seem to have scoured the landscape. Scientists now believe that billions of years ago Mars had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. There may have been lakes, rivers, perhaps even an ocean in the northern lowlands. Now the surface water is either frozen, evaporated, or lost to space. Today, water still exists on Mars, but is locked in ice at the polar caps or buried as permafrost beneath the surface. The polar ice caps of Mars are beautiful and complex. They consist of water ice and, during winter, layers of frozen carbon dioxide or dry ice. As winter turns to spring in each hemisphere, the carbon dioxide ice sublimates directly into gas, shrinking the polar cap dramatically. The water ice remains year-round, and scientists have used radar instruments to peer beneath the surface near the poles, discovering vast reserves of buried ice that could potentially be used by future human explorers. Mars has been explored by more spacecraft than any other planet besides Earth. Dozens of missions have been sent to Mars, including orbiters that map the surface from space and rovers that drive across the Martian terrain, analyzing rocks and soil, searching for signs of past water and possible past life. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have sent back stunning images of the Martian landscape: rocky plains, layered cliffs, sand dunes, dried-up stream beds, and distant horizons under a butterscotch-colored sky. These missions have confirmed that Mars once had conditions that could have supported microbial life, though whether life ever actually arose on Mars remains one of the great unanswered questions. Mars holds a special place in human dreams of space exploration. It is close enough to be reachable with current technology, and it has resources like water ice that could potentially support human settlements. The challenges are enormous: the thin atmosphere, the cold temperatures, the toxic soil containing perchlorates, the intense radiation from space, and the psychological challenges of isolation. But Mars represents the next frontier, the next world humans might visit and perhaps one day call a second home. Part 7: Between Worlds, the Asteroid Belt and Dwarf Planets. Beyond the orbit of Mars, as we travel farther from the Sun, we enter a region of the solar system filled with countless small worlds, a band of rocky and metallic objects that circle the Sun between Mars and Jupiter. This is the asteroid belt, a vast collection of debris left over from the formation of the solar system, remnants that never gathered together to form a planet. Here, in this quiet expanse, drift hundreds of thousands of asteroids, along with several dwarf planets, small worlds that are large enough to be rounded by their own gravity, but not large enough to clear their orbital paths of other objects. The asteroid belt is not densely packed as it often appears in movies and illustrations. In reality, the asteroids are spread across an enormous volume of space, separated by vast distances. If you were to travel through the asteroid belt in a spacecraft, you would likely see nothing but empty space for most of the journey, with asteroids appearing only occasionally as distant points of light. The total mass of all the asteroids combined is less than the mass of Earth's moon, a reminder that most of the material in the early solar system was swept up into the planets, leaving only these scattered fragments behind. Asteroids come in many sizes, from tiny pebbles only meters across to massive bodies hundreds of kilometers in diameter. Most asteroids are irregular in shape, tumbling through space as they orbit the Sun. They have not had enough gravity to pull themselves into spheres, so they remain jagged and lumpy, scarred by billions of years of collisions with other asteroids. Some asteroids are solid chunks of rock or metal, while others are loose collections of rubble held together by gravity, sometimes called rubble piles. The largest object in the asteroid belt is Ceres, a dwarf planet about 940 kilometers in diameter, roughly the size of Texas. Ceres is massive enough that its gravity has pulled it into a round shape, making it look more like a miniature planet than a typical asteroid. Ceres orbits the Sun at an average distance of about 414 million kilometers, taking about 4.5 Earth years to complete one orbit. The surface of Ceres is dark and heavily cratered, covered in a mixture of rock and ice. Spacecraft observations have revealed bright spots inside some craters, which appear to be deposits of salt left behind when water ice sublimated into space. Scientists believe that Ceres may have a layer of liquid water or briny mud beneath its icy crust, making it a potentially interesting place to search for simple forms of life. Another fascinating dwarf planet in the asteroid belt is Vesta, the second most massive object in the belt. Vesta is about 525 kilometers in diameter, smaller than Ceres but still substantial. Unlike Ceres, Vesta is not quite round, retaining a somewhat irregular shape. What makes Vesta particularly interesting is that it has a differentiated interior, meaning it once had a molten core that separated from a rocky mantle and crust, much like the terrestrial planets. This suggests that Vesta was hot enough in its early history to melt and differentiate, a process that requires significant internal heat. Vesta's surface shows evidence of ancient lava flows, and it has an enormous crater near its south pole, the result of a massive impact that sent debris to Earth as meteorites, allowing scientists to study pieces of Vesta directly in laboratories. Many asteroids are made primarily of rock, composed of silicate minerals similar to those found on Earth. These are called S-type asteroids, where the S stands for stony. Other asteroids, called C-type asteroids, are carbonaceous, meaning they contain carbon compounds and are darker in color. C-type asteroids are thought to be some of the most primitive objects in the solar system, relatively unchanged since they formed billions of years ago. A smaller number of asteroids are M-type, metallic asteroids composed largely of iron and nickel. These may be the exposed cores of larger bodies that were shattered by collisions, with their rocky outer layers stripped away. Some metallic asteroids contain valuable metals like platinum, gold, and rare earth elements, which has led to interest in the possibility of asteroid mining in the future. Asteroids orbit the Sun in much the same way that planets do, following elliptical paths and obeying the same laws of gravity. Most asteroids in the main belt orbit between about 2 and 4 astronomical units from the Sun, though some have orbits that bring them closer or take them farther. Asteroids that cross Earth's orbit are called near-Earth asteroids, and scientists monitor them carefully because a collision with Earth could cause significant damage. Over Earth's long history, many asteroids have struck our planet, some of them creating enormous impact craters. The most famous asteroid impact occurred about 66 million years ago, contributing to the extinction of the dinosaurs, it is believed. Spacecraft have visited several asteroids, flying past them, orbiting them, and even landing on them. The Near Shoemaker mission landed on the asteroid Eros in 2001. The Hayabusa missions visited asteroids Itakuwa and Ryugu, collecting samples and returning them to Earth. The OSIRIS-RX mission visited the asteroid Bennu, also collecting samples for return to Earth. These missions have revealed asteroids to be fascinating worlds in miniature, each with its own unique history, surface features, and composition. Up close, asteroids show boulders, craters, ridges, and sometimes even jets of gas and dust escaping from beneath the surface. The asteroid belt is not the only place where small worlds reside. Scattered throughout the solar system are other dwarf planets, objects large enough to be rounded by gravity but not massive enough to dominate their orbital neighborhoods. Beyond Neptune, in the distant Kuiper belt and even farther out, orbit dwarf planets like Pluto, Eris, Makemake, and Haumea. These icy worlds belong to a different population than the rocky asteroids of the inner solar system, but they share the designation of dwarf planet, a category created to recognize objects that are neither full-fledged planets nor mere asteroids. The study of asteroids and dwarf planets helps scientists understand the early solar system. These small worlds are time capsules, preserving materials and conditions from the solar system's formation. The asteroid belt and dwarf planets remind us that the solar system is filled with a vast diversity of objects, each one a world unto itself, each one part of the grand story of our cosmic neighborhood. Part 8, King of Planets, Jupiter and its realm. We journey now across a great gulf of space, leaving behind the rocky worlds and the asteroid belt, traveling outward to the realm of the giant planets. Here, more than 5 times farther from the Sun than Earth, orbits Jupiter, the largest planet in our solar system, a massive world of swirling clouds and powerful storms, with a retinue of dozens of moons. Jupiter is so large that all the other planets combined could fit inside it. It is a gas giant, a world with no solid surface, only layer upon layer of dense atmosphere transitioning gradually into liquid and compressed gas in the depths below. Jupiter orbits the Sun at an average distance of about 778 million kilometers, taking about 12 Earth years to complete one orbit. Despite its great size, Jupiter rotates remarkably quickly, spinning once on its axis in just under 10 hours. This rapid rotation makes Jupiter's day the shortest of any planet in the solar system. The fast spin causes Jupiter's equator to bulge outward and its poles to flatten slightly, giving the planet a noticeably oblate shape. The rapid rotation also drives powerful winds in Jupiter's atmosphere, creating the bands and zones of clouds that stripe the planet from pole to pole. Jupiter is enormous, with a diameter of about 143,000 kilometers at the equator, more than 11 times the diameter of Earth. Its mass is even more impressive. Jupiter contains more than twice the mass of all the other planets combined. If Jupiter had been about 80 times more massive, it would have had enough mass to ignite nuclear fusion in its core and become a star rather than a planet. As it is, Jupiter radiates more heat into space than it receives from the Sun, glowing faintly with internal heat left over from its formation billions of years ago. The visible surface of Jupiter is not a solid surface. The top layer of its thick atmosphere is composed mostly of hydrogen and helium, with traces of methane, ammonia, water vapor, and other compounds. The atmosphere is divided into alternating bands of different colors, light-colored zones where gas is rising and darker belts where gas is sinking. These bands are driven by convection and by Jupiter's rapid rotation, which stretches the rising and sinking regions into long stripes that wrap around the planet. The colors come from complex chemistry in the clouds, where sunlight and heat drive reactions involving sulfur, phosphorus, and organic compounds, creating the shades of white, cream, brown, orange, and red that we see. Jupiter's most famous feature is the Great Red Spot, an enormous storm that has been raging for at least several centuries, possibly much longer. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching speeds of about 450 kilometers per hour. The storm is enormous, currently about 16,000 kilometers across, large enough that Earth could fit inside it. The Great Red Spot appears reddish-brown, and scientists believe the color comes from complex organic molecules and possibly sulfur compounds that are brought up from deeper in the atmosphere and exposed to sunlight. Over the past century, astronomers have noticed that the Great Red Spot has been shrinking slowly, and it is now smaller than it was when it was first carefully observed in the 1800s. Jupiter has many other storms and atmospheric features, including smaller oval-shaped storms, lightning flashes, and auroras at the poles where charged particles from the Sun interact with Jupiter's magnetic field. The planet's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. This powerful magnetic field traps charged particles in vast radiation belts surrounding the planet, creating an environment that would be extremely hazardous to unshielded spacecraft and astronauts. Jupiter is attended by a large family of moons, at least 95 known as of recent counts, though many of these are small, irregular captured objects only a few kilometers across. The four largest moons are called the Galilean moons because they were discovered by Galileo Galilei in 1610 when he turned his telescope toward Jupiter. These four moons, Io, Europa, Ganymede, and Callisto, are worlds in their own right, each with unique characteristics and fascinating geology. Io is the innermost of the Galilean moons, orbiting very close to Jupiter. It is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly erupting and resurfacing the moon. Io's intense volcanic activity is driven by tidal heating. As Io orbits Jupiter, the planet's immense gravity stretches and squeezes the moon, generating friction and heat in its interior. The volcanoes of Io spew sulfur and sulfur dioxide, creating colorful deposits of yellow, orange, red, and white across the surface, and sending plumes of gas hundreds of kilometers into space. Io has no impact craters because its surface is constantly being renewed by volcanic activity. Europa, the second Galilean moon, is covered in a smooth shell of water ice that is crisscrossed with cracks and ridges. Beneath this icy crust, scientists believe there is a global ocean of liquid water, perhaps 100 kilometers deep, kept liquid by tidal heating similar to what drives Io's volcanoes. Europa's ocean may contain more water than all of Earth's oceans combined, and it has stirred some excitement among astrobiologists and exobiologists as one of the most promising places in our solar system to search for life. The icy surface shows few craters, suggesting it is relatively young and that the ice is constantly being refreshed from below. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It has a surface of both dark, heavily cratered terrain and lighter, grooved terrain that appears to have been resurfaced by tectonic activity in the past. Ganymede is the only moon known to have its own magnetic field, and scientists believe it, like Europa, may have a subsurface ocean beneath its icy shell. Callisto, the outermost Galilean moon, is heavily cratered and appears to be geologically inactive. Its ancient surface is saturated with impact craters, a record of billions of years of bombardment. Despite its seemingly dead appearance, Callisto may also have a subsurface ocean, detected through subtle effects on Jupiter's magnetic field. Jupiter also has a faint ring system, though it is far less impressive than Saturn's rings. Jupiter's rings are made mostly of dust and small particles, probably debris knocked off the inner moons by micrometeorite impacts. The rings are thin and dark, difficult to see except in special viewing conditions. Jupiter has been visited by several spacecraft, including Pioneer, Voyager, Galileo, and Juno. These missions have revealed Jupiter to be a complex, dynamic world with intricate atmospheric circulation, a powerful magnetic field, intense radiation belts, and a diverse family of moons. The Juno spacecraft, currently orbiting Jupiter, has provided stunning close-up images of the planet's poles, showing swirling cyclones and intricate cloud patterns never before seen in such detail. Jupiter plays an important role in the solar system. Its enormous gravity influences the orbits of asteroids and comets, sometimes deflecting them away from the inner solar system and protecting Earth from impacts. Jupiter's presence also affected the formation and migration of planets in the early solar system, shaping the architecture we see today. In many ways, Jupiter is a guardian and a kingpin, a giant world whose influence extends throughout our cosmic neighborhood. Part 9, Ringed Wonder, Saturn and its Moons. We travel onward now, moving farther from the Sun, journeying beyond Jupiter to the sixth planet, a world of pale golden beauty crowned with the most spectacular rings in the solar system. This is Saturn, named for the Roman god of agriculture and time. A gas giant similar to Jupiter in composition but smaller, lighter, and graced with rings so bright and extensive that they can be seen even through a small telescope from Earth. Saturn is a world of wonders orbited by dozens of moons, each one unique and wrapped in an atmosphere of soft pastel colors that shift and swirl in the gentle light. Saturn orbits the Sun at an average distance of about 1,430,000,000 kilometers, nearly 10 times farther from the Sun than Earth. At this distance, sunlight is much dimmer and weaker than on Earth, and temperatures in Saturn's upper atmosphere drop to about -140 degrees Celsius. Saturn takes about 29.5 Earth years to complete one orbit around the Sun, meaning that each season on Saturn lasts more than 7 Earth years. Saturn rotates quickly on its axis, completing one rotation in just over 10.5 hours, only slightly slower than Jupiter. This rapid rotation, combined with Saturn's low density, causes the planet to bulge significantly at the equator, making it the most oblate of all the planets. Saturn is the second largest planet in the solar system, with an equatorial diameter of about 120,000 kilometers, roughly 9 times the diameter of Earth. Despite its great size, Saturn has a surprisingly low density. In fact, Saturn is the least dense of all the planets, with an average density less than that of water. If you could find an ocean large enough, Saturn would float. This low density tells us that Saturn is composed mostly of hydrogen and helium, the lightest elements, with only a small core of heavier materials deep in the interior. The atmosphere of Saturn, like Jupiter's, is divided into bands and zones, though the colors are much more subdued. Saturn's clouds are pale shades of gold, cream, and butterscotch, with occasional wisps of white and subtle gradations of tan. The muted colors come from hazes of ammonia crystals and other compounds high in the atmosphere that soften and diffuse the light. Beneath these hazy layers, deeper clouds of water ice and ammonium hydrosulfide create additional structure, though these are mostly hidden from view. Saturn's atmosphere is calmer than Jupiter's in some ways, with fewer large storms visible at any given time. But occasionally massive storms do erupt, encircling the planet with bright white clouds before gradually fading away. Saturn radiates more heat into space than it receives from the Sun, just as Jupiter does. This internal heat comes partly from leftover warmth from the planet's formation and partly from a process called helium rain. Deep inside Saturn, where pressures are immense, helium droplets form and slowly sink toward the core, releasing gravitational energy as heat. This process has been gradually separating helium from the hydrogen in Saturn's interior over billions of years. The most striking feature of Saturn is, of course, its magnificent ring system. The rings extend outward from the planet for hundreds of thousands of kilometers but are remarkably thin, in most places only about 10 meters thick. Despite their thinness, the rings are bright and visible because they are made of countless particles of water ice, ranging in size from tiny grains like dust to chunks as large as houses or even mountains. Each particle orbits Saturn independently, following its own path, but together they create the appearance of solid, continuous rings. Saturn's rings are divided into several main sections, separated by gaps where gravitational interactions with Saturn's moons have cleared out particles. The most prominent rings, called the A and B rings, are the brightest and most massive. Between them lies the Cassini division, a gap about 4,800 kilometers wide, named after the astronomer Giovanni Cassini who discovered it in 1675. Inside the B ring is the C ring, much darker and more transparent. Beyond the A ring lies the faint F ring, narrow and kinked, shepherded by small moons that orbit just inside and outside it, keeping the particles confined. Even farther out are the extremely faint and tenuous E and G rings, made of tiny ice particles ejected from moons. Scientists believe Saturn's rings may be relatively young in cosmic terms, perhaps only a few 100 million years old. They may have formed from the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces, or from debris left over after a collision between moons. Over time, the rings are slowly being pulled into Saturn by its magnetic field and gravity, raining down onto the planet's atmosphere as a fine mist. Eventually, millions of years in the future, the rings may disappear entirely, leaving Saturn as unadorned as Jupiter or Neptune. Saturn has a large family of moons, at least 146 known as of recent counts, though many are small, irregular objects. The moons of Saturn are incredibly diverse, ranging from tiny moonlets embedded in the rings to massive Titan, the second largest moon in the solar system. Many of Saturn's moons interact with the rings, creating waves and gaps through gravitational resonances, and some moons even orbit within the rings themselves, carving out lanes and gathering material around them. Titan is the crown jewel of Saturn's moons, a world larger than the planet Mercury, with a thick atmosphere and a complex surface hidden beneath orange haze. Titan is the only moon in the solar system with a substantial atmosphere, composed mostly of nitrogen with a small percentage of methane and traces of other organic compounds. The atmospheric pressure at Titan's surface is about 1.5 times that of Earth's atmosphere at sea level. The thick atmosphere creates a greenhouse effect, but Titan is so far from the Sun that even with this warming, surface temperatures remain around -179 degrees Celsius. Beneath Titan's hazy atmosphere lies a landscape unlike any other. There are lakes and seas filled not with water but with liquid methane and ethane, hydrocarbons that remain liquid at Titan's frigid temperatures. There are river channels carved by flowing methane, and rain falls from methane clouds. There are vast dune fields made of organic particles, and ice mountains and hills made of water ice, which at Titan's temperatures is as hard as rock. Scientists believe that beneath Titan's icy crust lies a subsurface ocean of liquid water mixed with ammonia, making Titan another potentially habitable environment in the outer solar system. Another fascinating moon is Enceladus, a small, icy world only about 500 kilometers in diameter. Enceladus is highly reflective, covered in fresh, clean ice that makes it one of the brightest objects in the solar system. Near Enceladus's south pole are strange warm regions marked by long fractures nicknamed tiger stripes, where the ice is cracked and geologically active. From these fractures, enormous geysers of water vapor and ice particles spray out into space, creating a plume that reaches hundreds of kilometers high. This plume feeds Saturn's E-ring with fresh ice particles. The geysers indicate that beneath Enceladus's icy shell lies a global ocean of liquid water, kept warm by tidal heating from Saturn's gravity. The discovery of this ocean, along with organic molecules and other ingredients necessary for life detected in the plume, makes Enceladus another of the most exciting places to search for extraterrestrial life. Other notable moons include Mimas, with its enormous crater that makes it resemble the Death Star from Star Wars, Iapetus, with one hemisphere bright white and the other dark as coal, a stark contrast that scientists are still working to fully explain, and Hyperion, a sponge-like, irregularly shaped moon that tumbles chaotically in its orbit. Each moon has its own story, its own geology, its own mysteries. Saturn has been visited by 4 spacecraft: Pioneer 11, Voyager 1, Voyager 2, and the Cassini mission, which orbited Saturn from 2004 to 2017. Cassini provided an extraordinary wealth of data, studying the rings in unprecedented detail, discovering new moons, observing storms and seasonal changes in the atmosphere, and making close flybys of Titan and Enceladus. At the end of its mission, Cassini was deliberately plunged into Saturn's atmosphere to avoid any risk of contaminating the potentially habitable moons. The spacecraft's final transmissions provided unique data about Saturn's atmosphere and magnetic field before it was destroyed by the intense heat and pressure. Saturn, with its serene beauty, its glorious rings, and its diverse family of moons, reminds us of the elegance and complexity of the solar system. It is a world that invites contemplation, a world that seems almost too beautiful to be real. Yet it is real, orbiting the Sun in the cold outer reaches of our cosmic neighborhood. Part 10. Ice Giants. Uranus and Neptune in the outer dark. We journey now to the farthest reaches of the major planets, traveling far beyond Saturn into the cold, dark outer solar system. Here, billions of kilometers from the Sun, orbit the ice giants, Uranus and Neptune, the 7th and 8th planets. These worlds are smaller than Jupiter and Saturn, but still much larger than Earth. They are called ice giants not because their surfaces are icy, but because their interiors contain large amounts of water, methane, and ammonia in high-pressure forms, sometimes described as ices even though they exist as hot, dense fluids deep below the cloud tops. Uranus and Neptune are distant, mysterious worlds, visited only once by a spacecraft, yet they hold their own quiet wonders. Uranus orbits the Sun at an average distance of about 2,870,000,000 kilometers, roughly 19 times farther from the Sun than Earth. At this distance, sunlight is faint and weak, taking about 2 hours and 40 minutes to reach the planet. Uranus takes 84 Earth years to complete one orbit, meaning that each season on Uranus lasts about 21 years. Uranus has a most unusual characteristic. Its axis of rotation is tilted 98 degrees, meaning the planet essentially rolls on its side as it orbits the Sun. This extreme tilt means that during parts of its orbit, one pole points almost directly at the Sun while the other pole is plunged into decades of darkness. Then, as Uranus continues in its orbit, the situation reverses. No one knows for certain why Uranus rotates this way, but scientists believe the planet may have been knocked onto its side by a massive collision early in the solar system's history. Uranus is the third largest planet in the solar system, with a diameter of about 51,000 kilometers, roughly 4 times the width of Earth. The planet rotates fairly quickly, completing one rotation in about 17 hours. Uranus is composed mostly of a thick mantle of water, methane, and ammonia surrounding a small rocky core, all wrapped in an atmosphere of hydrogen, helium, and methane. It is the methane in the upper atmosphere that gives Uranus its distinctive pale blue-green color. Methane absorbs red light and reflects blue and green light, creating the planet's cold, serene hue. The atmosphere of Uranus appears relatively calm and featureless compared to Jupiter and Saturn, with only subtle banding and very few visible storms. This calmness is partly because Uranus radiates almost no internal heat into space, unlike the other giant planets. It generates only a tiny amount of internal heat, and most of the warmth in its atmosphere comes from the distant Sun. Scientists are not entirely sure why Uranus has so little internal heat. One possibility is that the collision that tilted the planet also disrupted its interior, allowing heat to escape more easily. The low internal heat means there is less convection and fewer dramatic weather patterns, giving Uranus its tranquil appearance. Despite its calm appearance, Uranus does have weather. Clouds occasionally appear in the upper atmosphere, and winds blow at speeds of up to 900 kilometers per hour in some regions, among the fastest winds in the solar system. The planet's extreme tilt creates unusual seasonal patterns. When one pole faces the Sun, that hemisphere receives continuous sunlight for years, warming slowly, while the opposite hemisphere remains in continuous darkness. This should create enormous temperature differences. But surprisingly, Uranus seems to maintain fairly uniform temperatures across its surface, suggesting that winds and atmospheric circulation efficiently redistribute heat. Uranus has a magnetic field, but it is tilted and offset from the planet's center in a peculiar way. The magnetic axis is tilted about 59 degrees from the rotation axis, and the magnetic field is not centered on the planet's core but offset significantly. This creates a lopsided, tumbling magnetic field that wobbles as the planet rotates, unlike the relatively stable magnetic fields of Earth or Jupiter. Scientists are still working to understand the internal structure that could produce such a strange magnetic field. Uranus has a faint ring system, much darker and less prominent than Saturn's rings. The rings were discovered in 1977 when astronomers observed Uranus passing in front of a star and noticed that the star's light blinked on and off several times before and after the planet itself blocked the star. This indicated the presence of thin rings surrounding the planet. Uranus has 13 known rings, most of them narrow and dark, made of small particles and chunks of rock and ice. The rings are thought to be relatively young, perhaps formed from the breakup of moons or from material that never coalesced into moons. Uranus has at least 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among solar system objects. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are composed of roughly equal parts rock and ice. Miranda, the smallest of the 5 major moons, has one of the most bizarre and varied surfaces of any moon. With a patchwork of different terrains including grooved regions, cratered plains, and towering cliffs. One cliff on Miranda rises about 20 kilometers high, taller than any cliff in the solar system. Scientists believe Miranda's strange appearance may result from a catastrophic collision that shattered the moon, which then reassembled in a jumbled configuration. Neptune, the 8th and outermost major planet, orbits at an average distance of about 4,500,000,000 kilometers from the Sun, roughly 30 times Earth's distance. At this remote distance, sunlight takes more than 4 hours to arrive, and the Sun appears as little more than a very bright star in Neptune's sky. Neptune takes 165 Earth years to complete one orbit, meaning it has only completed one full orbit since its discovery in 1846. Neptune rotates once about every 16 hours. Neptune is slightly smaller than Uranus, with a diameter of about 49,000 kilometers. But it is more massive, containing more material packed into a slightly smaller volume. Like Uranus, Neptune is composed of a thick mantle of water, methane, and ammonia surrounding a rocky core, wrapped in an atmosphere of hydrogen, helium, and methane. Neptune appears a deeper, richer blue than Uranus, also due to methane in its atmosphere, though scientists believe there may be an additional, unknown component that enhances Neptune's vivid color. Unlike Uranus, Neptune is a dynamic, active world with visible weather systems and powerful storms. The planet radiates more than twice as much heat into space as it receives from the Sun, indicating a strong internal heat source. This internal heat drives vigorous atmospheric circulation, creating some of the fastest winds in the solar system, with speeds reaching up to 2,000 kilometers per hour. When Voyager 2 flew past Neptune in 1989, it observed a large dark storm in the southern hemisphere, dubbed the Great Dark Spot, similar in some ways to Jupiter's Great Red Spot but more transient. Later observations from the Hubble Space Telescope showed that the Great Dark Spot had disappeared, replaced by other storms appearing and fading over time. Neptune also has white, wispy clouds of methane ice crystals floating high in the atmosphere, casting shadows on the cloud layers below. These clouds are driven by powerful updrafts and are constantly changing, giving Neptune a more dynamic appearance than Uranus. The planet's deep blue color and bright white clouds create a striking, beautiful contrast. Neptune has a magnetic field similar to Uranus, tilted about 47 degrees from the rotation axis and significantly offset from the planet's center. This similarity between the two ice giants suggests that their unusual magnetic fields are a result of their internal structure, perhaps generated in a layer of electrically conductive fluid in the mantle rather than in the core. Neptune has a system of faint rings, discovered shortly before Voyager 2's arrival. The rings are thin and dark, and some of them contain brighter arcs where material is more densely concentrated. Neptune has at least 16 known moons. The largest, Triton, is a fascinating and unusual world. Triton is one of the coldest objects in the solar system, with surface temperatures around -235 degrees Celsius. Despite the extreme cold, Triton is geologically active, with geysers of nitrogen gas erupting from beneath the surface and spraying dark material high into the thin atmosphere. Triton's surface is young and varied, with few craters, indicating recent resurfacing. Scientists believe Triton may have been a dwarf planet from the Kuiper Belt that was captured by Neptune's gravity. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, which supports the capture hypothesis. Slowly, over millions of years, Triton is spiraling inward toward Neptune, and eventually it may be torn apart by tidal forces, potentially creating a spectacular ring system around the planet. Both Uranus and Neptune have been visited only once, by Voyager 2 in its grand tour of the outer solar system. Voyager 2 flew past Uranus in 1986 and Neptune in 1989, providing our only close-up views of these distant worlds. The spacecraft revealed complex atmospheres, ring systems, diverse moons, and strange magnetic fields, transforming these distant points of light into real, tangible worlds. Part 11, Worlds Beyond Worlds, the Moons and Satellites. Throughout our journey across the solar system, we have encountered not only planets but also a vast collection of moons, natural satellites that orbit the planets in graceful, patient paths. These moons are worlds in their own right, each with its own character, its own geology, its own story to tell. Some are tiny, irregular chunks of rock only a few kilometers across, captured asteroids or fragments from ancient collisions. Others are massive bodies larger than planets, with atmospheres, subsurface oceans, volcanic eruptions, and landscapes as complex and beautiful as any planet. Let us turn our attention to these satellite worlds, these companions that circle the planets and add depth and richness to our solar system. The planets of our solar system have at least 290 known moons among them, and new ones are still being discovered as our telescopes and spacecraft improve. The distribution is uneven. Mercury and Venus have no moons at all. Earth has one. Mars has two small moons, Phobos and Deimos. But the giant planets, Jupiter, Saturn, Uranus, and Neptune, have vast families of moons, ranging from dozens to well over 100 each. These outer moons are incredibly diverse, shaped by different formation histories, different compositions, and different interactions with their parent planets. Our own moon is special to us, the only other world that humans have walked upon. The moon is large compared to Earth, about 1/4 of Earth's diameter, making the Earth-Moon system almost like a double planet. The moon formed about 4.5 billion years ago in a violent event, when a Mars-sized object struck the young Earth, throwing debris into orbit that eventually coalesced into the moon. This origin story explains why the moon's composition is similar to Earth's outer layers, and why it has a relatively small iron core. The moon's surface is ancient, covered with craters from billions of years of impacts. The dark areas we see when we look at the moon are called Maria, a Latin word meaning seas, because early astronomers thought they were bodies of water. In reality, the Maria are vast plains of solidified lava that flowed across the surface between about 3 and 4 billion years ago, filling in the low-lying impact basins. The lighter areas, called highlands, are older and more heavily cratered, representing the moon's original crust. The moon has no atmosphere, no weather, and no geological activity today, so its surface changes only very slowly. altered only by the occasional impact of a meteorite and the gradual weathering caused by solar radiation and micrometeorite bombardment. The Moon's gravity affects Earth in profound ways. The Moon's pull creates tides in Earth's oceans, raising and lowering sea levels twice each day as the Earth rotates beneath the tidal bulges. The Moon's gravity also causes Earth's rotation to slow very gradually over time, lengthening our days by a tiny fraction of a second each century. In turn, as Earth's rotation slows, the Moon slowly drifts away from Earth, receding at a rate of about 4 centimeters per year. Billions of years in the future, the Moon will be much farther away, and Earth's days will be much longer. Moving outward to the giant planets, we find moons of astonishing variety. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are among the most fascinating objects in the solar system. Io's surface is constantly renewed by volcanic eruptions, making it colorful and dynamic, a world of sulfur and fire. Europa's icy shell hides a deep global ocean that may harbor life, a liquid water realm kept warm by tidal heating. Ganymede, the largest moon in the solar system, has its own magnetic field and a complex surface of ancient dark terrain and younger groove terrain. Callisto's ancient, cratered surface is a record of the solar system's violent early history, a world seemingly frozen in time. Saturn's moons are equally diverse. Titan stands out as a truly unique world, the only moon with a thick atmosphere, a nitrogen-rich envelope that creates a hazy orange sky and allows liquid methane to flow across the surface in rivers and collect in lakes and seas. Titan's atmosphere is so thick that the surface pressure is higher than on Earth, and the thick air would partially support a human's weight, meaning that with the right suit and wings a person might be able to fly through Titan's skies. The surface of Titan is hidden beneath the haze, revealed only by radar and infrared instruments. It shows a complex landscape of sand dunes made of organic particles, mountains and hills of water ice, river channels carved by liquid methane, and large lakes near the poles filled with hydrocarbons. Beneath the surface, a subsurface ocean of liquid water mixed with ammonia likely exists, making Titan another potentially habitable environment despite its frigid temperatures. Enceladus, another of Saturn's moons, is much smaller than Titan but no less remarkable. This small, icy moon is geologically active, with geysers erupting from fractures near its south pole spraying water vapor and ice particles hundreds of kilometers into space. These geysers have been observed directly by the Cassini spacecraft, which flew through the plumes and analyzed their composition. The plumes contain water, organic molecules, and salts, suggesting that beneath Enceladus's icy shell lies a warm, salty ocean in contact with a rocky core, an environment that could potentially support microbial life. The discovery of these geysers and the subsurface ocean has made Enceladus one of the highest priority targets for future exploration in the search for life beyond Earth. Other moons around Saturn include Mimas, with its enormous Herschel crater giving it a distinctive appearance, Tethys, with a huge canyon system wrapping around much of the moon, Dione, with bright ice cliffs and wispy terrain, Rhea, Saturn's second-largest moon, heavily cratered and ancient, Iapetus, with its striking two-toned coloration, one hemisphere bright white and the other dark as charcoal, and Hyperion, a sponge-like, irregularly shaped moon that tumbles chaotically in its orbit. Each of these moons has been shaped by different processes, from impacts and tidal forces to cryovolcanism and the deposition of dark material from elsewhere in the Saturn system. The moons of Uranus, as mentioned earlier, are named after characters from Shakespeare and Pope. Miranda, the smallest of the 5 major moons, has a surface so jumbled and varied that it looks as though the moon was shattered and reassembled. Towering cliffs, grooved terrain, cratered plains, and smooth regions all coexist on this small world. Ariel and Umbriel are mid-sized moons with different appearances, Ariel has relatively young terrain with valleys and ridges suggesting past geological activity, while Umbriel is dark and heavily cratered, with few signs of resurfacing. Titania and Oberon, the two largest moons of Uranus, have ancient, cratered surfaces with some evidence of past tectonic activity and possible cryovolcanism, where water or icy slush erupted onto the surface in the distant past. Neptune's largest moon, Triton, is one of the strangest and most interesting moons in the solar system. Triton orbits Neptune in a retrograde direction, moving opposite to the planet's rotation, which strongly suggests it was not formed in orbit around Neptune but was instead captured from elsewhere, probably from the Kuiper Belt. Triton is slightly smaller than Earth's moon but is much colder, with surface temperatures around -235 degrees Celsius, making it one of the coldest surfaces in the solar system. Despite the extreme cold, Triton is geologically active, with nitrogen geysers erupting from the surface, driven by seasonal heating from the weak sunlight. The surface is young, with few craters, and shows a variety of terrains including smooth plains, ridges, and a strange cantaloupe-like terrain of pitted and grooved regions. Triton likely has a subsurface ocean as well, kept liquid by tidal heating as it orbits Neptune. Over millions of years, Triton's orbit is slowly decaying, and eventually the moon will come close enough to Neptune that tidal forces will tear it apart, possibly creating a spectacular ring system that could rival or exceed Saturn's rings. Many of the smaller moons of the giant planets are irregular in shape, captured objects that were probably once asteroids or Kuiper Belt objects that wandered too close and were snared by the planet's gravity. These irregular moons often have eccentric, tilted orbits, and they sometimes orbit in retrograde directions. They are witnesses to the chaotic early solar system, when gravitational interactions were more common and the architecture of the planets and their moons was still being established. The study of moons has revealed that small worlds can be just as complex and geologically active as large planets. Tidal heating, caused by the gravitational pull of a massive planet stretching and squeezing a moon, can generate enough internal heat to drive volcanic activity, maintain subsurface oceans, and reshape surfaces. Impacts from asteroids and comets can fracture and crater these worlds, while ancient resurfacing events can erase old terrain and create new landscapes. Each moon is a unique experiment in planetary science, a world shaped by its particular history and circumstances. Part 12: Icy Visitors. Comets, meteors, and the distant reaches. Beyond the orbits of the planets, in the cold outer reaches of the solar system, lie vast reservoirs of icy objects, ancient remnants from the formation of the planets, frozen and preserved for billions of years. These are the comets, small icy bodies that occasionally fall inward toward the sun, warming and brightening as they approach, creating glowing tails that stretch across the sky. Comets are wanderers, visitors from the dark outer regions, and they have fascinated humanity throughout history. Let us explore these icy travelers, along with their smaller cousins the meteors, and the distant realms from which they come. Comets are often described as dirty snowballs, a simple phrase that captures their basic composition. They are made of water ice, frozen gases like carbon dioxide, methane, and ammonia, with dust and rocky particles mixed throughout. Most comets are only a few kilometers across, small and dark when they are far from the sun. But when a comet's orbit brings it close to the sun's warmth causes the ices to sublimate, turning directly from solid to gas without becoming liquid. This process releases gas and dust from the comet's surface, creating a glowing cloud around the nucleus called a coma, and often creating one or more tails that stream away from the sun. A comet typically has two tails. One tail, made of gas and called the ion tail, is pushed directly away from the sun by the solar wind, the stream of charged particles flowing outward from the sun. The ion tail glows with a bluish color as the gas is ionized and excited by sunlight. The other tail, made of dust particles released from the comet, is pushed away from the sun by the pressure of sunlight itself. The dust tail curves slightly as the particles follow their own orbits around the sun, and it often appears yellowish or white. Both tails can stretch for millions of kilometers, thereby qualifying comets as among the largest objects in the solar system by volume. Comets originate from two main regions in the outer solar system. Short-period comets, those that orbit the sun in less than about 200 years, come mostly from the Kuiper Belt, a region beyond Neptune filled with icy bodies. The Kuiper Belt extends from about 30 to 55 astronomical units from the sun, a vast, flattened disk of debris left over from the formation of the solar system. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across. Some of these objects, like the dwarf planet Pluto, are large enough to be rounded by their own gravity. Long-period comets, those that take hundreds, thousands, or even millions of years to orbit the sun, come from the Oort cloud, a vast spherical shell of icy objects that surrounds the entire solar system at immense distances. The Oort cloud begins at about 2,000 astronomical units from the sun and extends outward to perhaps 100,000 astronomical units, nearly halfway to the nearest star. At these distances, the sun is just a bright point of light, and the comets drift in the cold darkness. Occasionally, a passing star or the gravitational influence of the Milky Way galaxy nudges an Oort cloud comet, sending it falling inward toward the sun. When a comet approaches the inner solar system for the first time, it may be pristine, its ices never before exposed to the sun's warmth. As it rounds the sun and heats up, it becomes active, releasing gas and dust and developing its coma and tails. Some comets are so bright they can be seen in daylight. Others are faint and require telescopes to observe. After passing the sun, the comet swings back outward, cooling and fading. Some comets return on predictable schedules, like Halley's Comet, which orbits the sun every 76 years. Other comets are seen only once. Comets have played an important role in the history of the solar system. In the early days, when the planets were still forming, comets and icy bodies bombarded the inner solar system, delivering water and organic molecules to the young planets. Some scientists believe that much of Earth's water came from comets, though recent studies suggest asteroids may have been a more important source. Regardless, comets certainly contributed to the inventory of volatile materials on the terrestrial planets. Comets are also responsible for meteor showers, those beautiful displays of shooting stars that occur at certain times each year. As a comet orbits the sun, it leaves behind a trail of dust and small particles along its path. When Earth's orbit intersects this trail, the particles enter Earth's atmosphere at high speed, heating up through friction and glowing brightly as they vaporize, creating streaks of light across the sky. These are meteors, often called shooting stars. Most meteors are tiny, no larger than a grain of sand, but they move so fast that they create brilliant flashes. Larger pieces of debris, called meteoroids, can survive the passage through Earth's atmosphere and reach the ground as meteorites. Meteorites are fragments of asteroids or, more rarely, comets that have fallen to Earth. Scientists study meteorites carefully because they are samples of the solar system's raw materials, unchanged since they formed billions of years ago. Some meteorites are rocky, some are metallic, and some are a mixture of rock and metal. Spacecraft have visited several comets up close, revealing them to be dark, irregularly shaped objects with complex surfaces. The Giotto spacecraft flew past Halley's Comet in 1986. The Rosetta mission orbited Comet 67P Churyumov-Gerasimenko for 2 years, studying it in detail and even landing a small probe on its surface. These missions showed that comet nuclei are darker than coal, with surfaces covered in dust, rock, and organic material. Comets, meteors, and the distant Kuiper Belt and Oort cloud remind us that the solar system is far larger than the realm of the planets. These icy bodies are leftovers from the formation process, preserved in the cold outer regions for billions of years. They are messengers from the past, carrying information about the early solar system. Part 13, Reaching Outward, Human Exploration and Discovery. For most of human history, the solar system was a mystery, visible only as points of light moving across the night sky. The planets were wandering stars, the moon a glowing disk, the sun a source of light and warmth whose true nature was unknown. Ancient peoples observed the heavens carefully, tracking the movements of celestial objects, creating calendars, and weaving stories to explain what they saw. But the true nature of the solar system remained hidden. Let us reflect on how humanity has gradually come to understand the solar system, how we have reached outward with telescopes and spacecraft, and how each discovery has deepened our sense of wonder. The first great leap in understanding came with the invention of the telescope in the early 1600s. When Galileo Galilei turned a simple telescope toward the sky in 1609, he saw things no human had ever seen before. He observed mountains and craters on the moon, revealing it to be a world with topography, not a smooth sphere. He discovered 4 moons orbiting Jupiter, proving that not everything in the cosmos circled Earth. He saw that Venus went through phases like the moon, indicating it orbited the sun. These observations provided strong evidence for the heliocentric model, the idea that the planets orbit the sun rather than everything orbiting Earth. Over the following centuries, telescopes grew larger and more sophisticated, revealing ever more detail. Astronomers discovered Uranus in 1781, Neptune in 1846 through mathematical predictions, and Pluto in 1930. They observed the clouds of Jupiter and the rings of Saturn. They tracked asteroids and comets. They measured the distances to the planets and began to understand the true scale of the solar system. Each discovery was a triumph of human curiosity and ingenuity, a step toward comprehending our place in the cosmos. But observing from Earth has limitations. The atmosphere distorts and blurs images, and some wavelengths of light are absorbed before they reach the ground. To truly explore the solar system, humanity needed to leave Earth, to send instruments into space where they could observe without interference and travel to other worlds to study them directly. The space age began in 1957 when the Soviet Union launched Sputnik, the first artificial satellite. This small metal sphere, orbiting Earth and transmitting radio signals, marked the beginning of a new era of exploration. In the decades that followed, spacecraft were sent throughout the solar system, transforming distant points of light into real, tangible worlds. The first missions were simple flybys, spacecraft passing near planets and moons at high speed, taking photographs and measurements during brief encounters. The Mariner missions explored Venus, Mars, and Mercury in the 1960s and 70s. The Viking landers touched down on Mars in 1976, testing the soil for signs of life and sending back the first color images from the Martian surface. The Voyager missions, launched in 1977, embarked on a grand tour of the outer solar system, visiting Jupiter, Saturn, Uranus, and Neptune over 12 years. Voyager 1 and Voyager 2 sent back stunning images of the giant planets, their rings, and their moons, revealing worlds of astonishing diversity and beauty. These spacecraft discovered active volcanoes on Io, hints of subsurface oceans on Europa, the complex weather systems of Jupiter and Neptune, and the geysers of Triton. The Voyagers also carried golden records, messages from humanity containing sounds, images, and music. Both Voyagers have now left the solar system, crossing into the space between the stars. Other missions followed, each one designed to answer specific questions. The Galileo spacecraft orbited Jupiter from 1995 to 2003. The Cassini mission orbited Saturn from 2004 to 2017, revolutionizing our understanding of the ringed planet. The New Horizons spacecraft flew past Pluto in 2015, showing the dwarf planet to be a geologically complex world with mountains of water ice and plains of nitrogen ice. Closer to home, Mars has been explored extensively by a fleet of orbiters, landers, and rovers. The Mars exploration rovers, Spirit and Opportunity, operated for years beyond their planned missions. Curiosity, a car-sized rover that landed in 2012, has climbed partway up Mount Sharp. Perseverance, which landed in 2021, is collecting samples that may one day be returned to Earth. These rovers have confirmed that Mars once had liquid water on its surface and that ancient Mars had conditions that could have supported microbial life. Robotic exploration has not been limited to the planets. Spacecraft have visited asteroids, landing on them and even returning samples to Earth. The Hayabusa missions collected samples from asteroids. The OSIRIS-RX mission collected samples from the asteroid Bennu and returned them to Earth. These samples contain organic molecules and water-bearing minerals, providing insights into the materials that formed the planets. Telescopes, both on the ground and in space, continue to expand our understanding. The Hubble Space Telescope, launched in 1990, has observed the solar system for decades. The James Webb Space Telescope, launched in 2021, has begun observing the solar system in infrared wavelengths. Human exploration of space has been limited so far to the region near Earth. 12 humans walked on the Moon between 1969 and 1972 during the Apollo program. Since then, no human has traveled beyond low Earth orbit, but plans are underway to return humans to the Moon and eventually send astronauts to Mars. The exploration of the solar system is not just about gathering data. It is about wonder and inspiration. The images sent back by spacecraft remind us that we live in a universe far larger and more diverse than our everyday experience suggests. They inspire us to think beyond our immediate concerns, to consider deep questions about origins and existence. Part 14. Returning to Rest. A gentle closing under endless skies. We have traveled far, wandering through the vast spaces of our solar system, visiting each world in turn, from the blazing heart of the sun to the cold, distant ice giants. From the rocky surfaces of Mercury and Mars to the hidden oceans beneath Europa and Enceladus. We have seen storms that rage for centuries, volcanoes that erupt constantly, rings that encircle entire planets, and moons more numerous than we can easily count. We have followed comets on their long journeys, and we have remembered the spacecraft that have carried human curiosity outward. Think back for a moment to where we began, with the sun, that ancient star that has been shining steadily for more than 4.5 billion years. Remember the warmth of sunlight on your face, the way it illuminates the world, the way it sustains life on Earth. The sun is always there, even when we cannot see it, always burning, always giving. Let that steady presence comfort you now. Let the thought of the sun's patient light ease any tension you may be holding. Breathe slowly and feel yourself relaxing deeper. Remember Mercury, small and swift, racing around the sun, its surface scarred by ancient impacts, its long days and nights. Mercury endures extremes of heat and cold, yet it persists, orbiting faithfully, a silent companion to the sun. Let the image of Mercury, patient in its orbit, bring you calm. Remember Venus, wrapped in its thick clouds, turning slowly backward beneath a heavy atmosphere. Venus shines brilliantly in our sky, the evening star, the morning star, a beacon of light. Let the thought of Venus, bright and serene, soften your thoughts. Remember Earth, our blue home, covered with oceans and continents, wrapped in a thin atmosphere that makes all life possible. Earth is precious, a world of beauty and complexity. Let gratitude for our planet fill your heart. Let the image of Earth, turning gently in space, bring you peace. Remember Mars, the red planet with its vast deserts and towering volcanoes, its ancient river valleys and polar ice caps. Mars may once have been warmer and wetter. Today it is cold and dry, but it holds secrets still. Let the thought of Mars, quiet and patient, ease you toward deeper rest. Remember the asteroid belt, that region of small worlds drifting in their orbits. Remember Ceres, round and icy. These small worlds remind us that the solar system is filled with diversity. Let the image of the asteroids bring you tranquility. Remember Jupiter, the king of planets, enormous and powerful, with its swirling clouds and the great red spot. Remember Io, volcanic, Europa, with its hidden ocean, Ganymede and Callisto. Jupiter and its moons are a system unto themselves. Let the thought of Jupiter, vast and majestic, fill you with quiet awe. Remember Saturn, the ringed wonder with its pale golden clouds and magnificent rings. Remember Titan, wrapped in orange haze with methane lakes, and Enceladus, with geysers shooting water into space. Saturn is a world of elegance and grace. Let the image of Saturn, serene and glowing, ease you into deeper relaxation. Remember Uranus, tilted on its side, rolling through space in its long orbit, its pale blue-green disk calm and quiet. Remember its moons and faint rings. Uranus is a world of mystery, distant and cold. Let the thought of Uranus bring you peace. Remember Neptune, the deep blue giant, dynamic and active, with powerful winds and bright white clouds, and Triton, with nitrogen geysers. Neptune is the outermost major planet. Let the image of Neptune ease you toward sleep. Remember the many moons we have visited, from our own moon to the exotic moons of the outer planets. Remember the subsurface oceans, the volcanic eruptions, the icy surfaces. These moons remind us that wonder exists everywhere we look. Remember the comets, those icy wanderers from the outer reaches, falling inward toward the sun and brightening, their tails streaming across the sky. Remember the meteors, creating brief flashes of light. Remember the Kuiper belt and the Oort cloud. These distant realms remind us that the solar system extends far beyond the planets. Remember the spacecraft and telescopes, the human ingenuity and curiosity that have allowed us to explore these distant worlds. Remember that we are part of this story, that we live in an age of discovery. As you rest now, let all of these images blend together in your mind, a gentle tapestry of worlds and moons, rings and clouds, sunlight and shadow. Let yourself feel connected to the solar system, to the vast cosmic neighborhood in which we live. You are made of the same elements that formed in ancient stars. You are part of this universe. Let that connection bring you comfort and peace. Breathe slowly and deeply. Feel your body relaxing completely. Let any remaining thoughts drift away. There is nothing you need to do, nowhere you need to be. You are safe, you are comfortable. Imagine yourself floating gently in space, looking back at the solar system from a great distance. You can see the sun, a bright point of light at the center, and the planets arrayed around it. Everything is peaceful. Everything is in motion, yet everything is still. The solar system turns in the darkness, patient and eternal, and you are part of it. Let yourself drift now. Let sleep come naturally, softly, like night falling over a quiet landscape. There is no rush. Simply allow yourself to sink deeper into rest, carried by the gentle rhythm of your breathing, surrounded by the images of the worlds we have visited together. The solar system will still be there tomorrow. Tonight it is enough to rest, to sleep, to dream peacefully.